Okay, so we looked at exercise 12.2.2 and we looked at part A. If the equation y squared equals x cubed plus ax plus b has a double or triple root, then 4a cubed plus 27b squared equals 0. So we went through the problem, and basically there are two cases, double or triple root. Here we do the double root case. In this case, then there are two roots, R1 and R2. Written R1 as a double root, so I can just algebraically express x cubed plus ax plus b as this expression here. It just shows that this has a double root. Then you work it out and get the relation you need. Now I'm just going to, for you people who are listening to the recording, I'm just going to let you look at this because Amanda and I went through this, and I don't want to bore her. So let's go back. We're now thinking about part B. So now we can slow down and do part B. So you want to show that if this is true, if 4a cubed plus 27b squared equals 0, then the equation y squared equals x cubed plus ax plus b has a double or triple root. So you certainly want to use a similar method. But how exactly do you do that? So let me take it to Amanda. What would you do? Are you there, Amanda? Hello? Hello? Yes, I can hear you now. Yes. I just couldn't for a second. Yeah. Okay. Okay, yeah, go ahead. No, you can't assume that. You can't assume that. The only thing you can assume is this. That's the only thing you can assume. But you really do want to do something similar. Here what we did was we could write for x cubed plus ax plus b in this way because we knew that there's a double root. Now in this case we don't know anything. So let's just copy this. But we can't write this like this anymore because we don't know it has a double root. But how can we write it? Well, you can't say this equals 4a cubed plus 27b squared. Well, you could, but that's not helpful. But what you want to do is write, you know that this has three roots, so you know you can factor it. So how would you write it in general as a product of, so you know you can write it as a product of three terms. So what should I write? It should be similar to this, except you don't know that there's a double root. Yeah, that's good. Then FOIL it all out, yes. Well, it's not that bad. It's not that bad. Why don't I let you try this? I think it's a little more complicated than this, but it's going to be this. It's going to be the very same process. But this time, instead of going from R to A and B, you're going from A and B to R1, R2, R3. So you're still going to get three equations. This time you're going to have three equations in 5 unknowns, which is not fun. But anyway, then you'll want to use those equations to eliminate well, you want to use those equations to get some relation between R1, R2, and R3. So let me let you do that and see if you can. I mean, that's the strategy. And no, you can't assume anything. That's what you want to show. You'll want to show that two of these must be equal. That's what you'll want to show. So try it. If you run into trouble, then you can email me and we can see where to go from there. But I don't want to spend the whole time on this because we've got other questions too. All right. Well, let's. All right. Well, so does this section have a video? Maybe it doesn't. It looks like it doesn't. Well, maybe I need to make one. I think, no, there's no video symbol. Well, maybe, why don't I just quickly go over what it's talking about. It seems that right at this point you might wonder, what do elliptic curves have to do with cryptography?
I was actually very curious about it.
Well, let's go back here and I can kind of get you a relation. In this case, the whole thing about cryptography, whoops, did I lose you? Okay, it's stopped. Okay, the whole thing about cryptography is that you need this so-called one-way function. It's a function that's easy to compute but hard to invert. And the elliptic curves are going to give you a one-way function. So if you remember how this works, you can, in order to, let's see, how does this work? I think for the first part, yeah, you can upload that too. So let's see all right, so welcome Adam. So remind me what the questions were on section 1. Okay. All right, so 12.1.1 is a proof. You're not going to need a spreadsheet for that. And I think that's just, yeah, okay. All right, so then, let's see. So you said 12.1.3, 12.1.4. All right, so here you just need to compute, you're going to be computing big powers. So the idea here is that this so-called discrete logarithm, if you know let's see if I need to get this right. It's easy to compute the discrete logarithm, but if you know what the discrete logarithm is, it's hard to find out what it was. So for instance, suppose you know that the discrete logarithm is 4. Then to find the original number is hard. So that's the idea. You want a function that goes one way easily and the other way it goes hard. And that's what the elliptic curve is going to give you. So, Adam, did you have any trouble with section 1?
I just have to go back to my
That is basically what the issue is. Yeah. But I think it's pretty clear you have the base and the power and the mod. So they're just three numbers to figure out. So let's take a look here then at the cryptography. Elliptic curve. All right. So here we've got elliptic curve. So you asked me this question about. All right. So what you're doing here is you're defining a group based on these curves, and the points on the curves are the group elements. And this group and the group operation is this geometrical construction. So again, my group elements are points on the curve, and if I want to find, and the group operation is called plus, and if I want to find the plus of two group elements, I take the 2 points on the curve, then I draw the line that joins them, and that's going to intersect the curve at exactly one other point. Then I take that other point and reflect it, and that gives me P1 plus P2. So I think this picture is pretty clear. So the curve, some of these curves look pretty different, but it turns out that no matter whenever you choose 2 points on the curve, then you'll always get a third point when you draw the line between them and intersect. In this case, yeah. Well, yeah, it does, yeah, but it's not, it's a secant line. It's a, yeah, it's a secant line, but what you're looking at is not the derivative, but the third point that it hits. That's something that's not true for a general function, but it turns out for these elliptic curves, whenever you draw a secant line, the secant line is going to hit the curve somewhere else. And what you do, you have to remember that you go and you hit the curve somewhere else, and then you reflect it in the x-axis. So P1 plus P2 wouldn't be down here. It's up. But it's off the page because it's too far away. And if you could have 1 point on this egg and 1 point on this hyperbola sort of thing, and still, if you do 1 point here, 1 point here, it's still going to intersect. Well, in this case, it will intersect the egg somewhere else. You'll always get exactly one more point. And that's a property of cubic curves. We don't prove that, but that just turns out to be true. And then, so you can imagine that computing this third point basically involves some kind of calculus. You need to figure out this line, you need to figure out the point of intersection, and then you need to reflect it. So that's what these steps are going through. You compute the slope, and then you use point slope formula to get you the secant line, and then that gives you, and then you do some other algebra to get the point of intersection, and then you reflect. So I think that let's see. I don't even know if I assigned this. But anyway, I do remember that I think here I ask you to go through the calculation for several points. I did assign a couple of. I assigned number 7. Okay, right. I think just number 7. Right. Okay. So if we look through this, it says x1 plus x2 plus x3 equals m squared, or x1, x2, x3 are the x coordinates of the 3 intersections of A. This exercise will prove this. So this is going to be some other algebra proof, just like the one that we we did at the beginning of this session. So let me let you look at that, and if you have trouble, we can talk about it later. But it's going to be an algebra proof, pretty much like this one. All right, so let's go back, and then let's see. And so here's some different examples. I think you can follow the examples and see how it's computed. Now, all this is preliminary because, in fact, Amanda, your comment was very relevant, because what you do in elliptic curve cryptography is you don't just add any 2 points. You take 1 point and keep adding it to itself. And if you add 1 point to its, yes, it's repeated addition. Now, when you add 1 point to itself, you don't have 2 different points. You have the same point, but then you take the tangent line. In fact, you take the tangent line. So if I wanted to double this point P2, I would take the tangent line through P2. It's going to be kind of like this. And depending on exactly where P2 is, in fact, I think at the point of inflection here, that will be exactly tangent to this point here. Or if I took this point here and I took the tangent, it's going to go at this one here. And that's what they're calling point doubling. And then I think I didn't I assign this one? Okay. All right, so you're lucky then. Oh, okay. Okay. All right. Well, a lot of this is very algebraic. It's working out that these relations actually work. All right. So you're going to need M in order to figure out the sum, because you have to find the tangent line. So once you found the tangent line, then you can find the x coordinate of the other intersection. This one here? Okay. Well, let's see. Would it be the quotient rule? Well, here it says take the derivative of e and solve for dy dx. So let's go back to e. Yeah. Yes, m is the derivative. Yeah. Let's see where e is. Well, yeah, e is the expression where you put everything on one side, and you're looking for the roots e equals 0. Oops, where is e? Well, here you have all of these e's here. So e is you just take the equation and you differentiate. So you will have to use you're differentiating with respect to x. So you are going to have to use the chain rule. You will have to use the chain rule to differentiate y squared. So again, this is setting up the algebraic machinery so that you can do the problem. All right, let's see. Let's go down. And then there's this exceptional case where you actually have 2 points that are lined up vertically, and if you add those, then you get a vertical line. So there's technically there is no third intersection. So you add this so-called point at infinity.
Wouldn't you just get 0, right, if you just add those two, 'cause it's positive and negative?
Well, remember what you have to do. If you add this and this, you're supposed to take the curve here, the line here, and then find the point of intersection of that line with the curve. But it doesn't intersect the curve anymore. Right? If I take 2 points, if I take 1 point here and 1 point here, then the line through those two is going to intersect the curve down here. But if I take this point and this point, and I draw the line, it doesn't intersect the curve anywhere. So you just add a mathematical object. I mean, you know, mathematicians do this. When you can't find the square root of -1, so you just add another number. You just call it I. So in this case, if you can't find a point of intersection, you just add another point. You call it the point at infinity. And the point is that you don't distinguish positive infinity from negative infinity. You just call it point at infinity. All right. So again, that's setting up machinery, and then this part is showing that this actually gives you a group. We have our operation of addition, and you have to prove the whole stuff. You have to show closure, and then identity, and then inverse, and then associative. Now it turns out that the identity is just this point at infinity, which you can see by, for instance, if I take this point here. If I take this point and draw a line through this point in the point at infinity, well, that's just a vertical line. So if I draw the vertical line and intersect with a curve, then I get the point down below, which corresponds to my original point. And then when I reflect that, I get the original point. So you can see that in the picture here. If I have P and I draw the line to the point at infinity, then it intersects the curve down here. Then when I reflect it, I get P again. So that explains why P plus infinity equals P. On the other hand, if I take this point P and I take this point, which is the reflection down here, then the line takes me out to infinity. So this is actually the inverse of P. So you can think about that, but the upshot is that you do have an identity and an inverse related to this point at infinity. Then, let's see. So we go through the group properties. So we have a group. We have a group. And then the question is it a abelian group? I'll let you think about that. So the abelian means, does it matter if you take, if I take P1 plus P2, is that going to give me a different result from P2 plus P1? Or yeah. So think about that. So since it's going through the same points, that kind of is the idea there. So let's see. So what do we have here? So as I said, when we're doing cryptography, we're going to be adding the same point to itself to get many times. So I should tell Amanda this because apparently this wasn't clear. In this exercise here, 12.2.12, it's asking you to add repeatedly. But this P here is the P from the previous example, from the previous example. So, yes. Yeah, because in this example, you computed 2P, and then I'm asking you to, then I'm asking you to compute. Well, using the equations. You use the equations from here, but you don't use the points. You use the point from here. Because the point is that in 12 to 11 you found 2p, and then here you just add that to p. Now, I think that actually you can probably do this with a spreadsheet. Otherwise it may take you a while. But I would recommend you set up a spreadsheet to do this. So if we look at these equations here, you have to do your computations mod 17. I think we'll probably have to have another session to make sure, once you try this, to make sure it works out. Let me think. Saturday, so we need to talk about this. I like to be on around noontime, but I wonder if that time is okay for people. Mornings before 1 p.m. is the best time for me. Any day before 1 p.m. So I don't know if we can arrange something. Does Saturday morning work for you?
Yeah, Saturday morning works.
So what time?
You said noon.
Noon is good. Noon is fine. So let's just decide noon on Saturday. And we'll do that. So try it and see. Okay. Right. And then here as you do the so this diagram looks very similar to the one in the Diffie-Hellman chapter. It's just that you're using a different one-way function. In this case, your key. Let's see, what does he? You're using these points instead of using modular numbers. So let's see how this works. So let's see how this works here. So this is your base. You're doing your calculations mod 17, and this is your base point, which is the kind of the what anchors your cryptography system. So what the point of this is for them to get this shared pair of numbers, which nobody else knows, but they know. So how does this work? So he chooses n equal 4, so that means that he takes 4 times p, and p is public knowledge, and that gives, so he sends 3, 1. So I mean, what you can say here is that Moses makes a choice of n. This is a secret choice, nobody else knows. And Rachel makes a choice of m, which nobody else knows. And they used these two secret choices to come up with this pair that nobody else knows. Because Rachel knows the 8. She doesn't know the 4, but she knows the result. So she uses that 8 to compute this. And Moses, he doesn't know the 8, but he has the 8p. But he knows the 4, so he uses his knowledge to compute this. But other people don't know the 4 or the 8, so they can't do anything. They can't decode it. All right, so let me see. So did I assign anything in this section? Right. 14, 15. Okay, right, okay. So I assigned plenty in this section. So, well, this is where you really get to the cryptography part. This one is just key exchange. And key exchange is used when it's basically setting up your secret information exchange. But here's a full crypto system that you could use to send information. This is not about sending information. This is about sending a key, and you use the key to send information. But this is actually sending the information. I think what I'm going to do is make a video for this, because I think this takes some time to really absorb, and it may be hard to just read through it. Sorry, say again? Sure. Yes. Well, let's see. So you're finding that you're needing more time for this. Okay. Well, yeah. I wish that. Let me think about it. I think I certainly need to provide a little more support because there's no video here. So let me think about that. So I think that's my action item. Is I'm going to make a video for this section, especially this last part. And we'll meet on Saturday. And I think before then, try to work on the problems that I talked about. Well, we'll see how far you can get, how far you can get with this. All right, so I'm going to stop the recording.